Welcome to Dr. Jed's continuing calculus video series. Today's lesson is section 6.1 on Rogowski, area between curves. So the idea is fairly simple. We'll mention it, then we'll use that idea, do some examples. It's going to be just like that. So here's the idea. We want to find the area. This is not a signed area. We want to find the actual area between two functions, y equals f of x, y equals g of x. Here's my picture. So f kind of goes like this and comes down, g kind of goes like this. We want to find the area, that part plus that part. So we don't want a signed area. We don't want one of these to be positive, one to be negative. The area under f is going to be all of this. The area under g is all of this. And you see, there's overlap in these two. So if I take one of them minus the other, all of this goes away. So I'm going to integrate one of them, subtract the other. Now which is first? Sometimes it's f, sometimes it's g. I'm going to say we're going to integrate the top function minus the bottom function. And you just have to figure out which is which. We're going to integrate from a to b, where those are the endpoints on x. This is the whole area. This is exactly what we're going to do today. That's all we're going to do today. And let's try an example. So find the area between y equals x and y equals x squared. As I said in the formula, we need to know which one's the top one. So we'll draw a picture. These are easy functions. And there it is. There's one of them. That's y equals x. Here's the other. You don't have to be perfect at drawing. To notice now that there are actually, well, there are only two places they intersect. Hopefully you can guess what they are. It's 0 and 1. We're going to show how to find them first, of course, before we just assume it's 0 and 1. But it should also tell you that y equals x is the top. Y equals x squared is the bottom. We want this area. So first off, how do we find a and b? Well, if it's where the two things intersect, it's where this formula and this formula have the same y value. So it's where this and this are the same. So we set those equal. To find a and b, we set those equal. And, well, you could divide by x and get x equals 1, but that's not a good way to do it because, in this case, x can be 0 and you can't divide by 0. A better way to do it is to factor. Bring the x over, well, technically the x squared, but then multiply by minus 1, whatever. We'll factor this, and we get x equals 0 or 1. Those are our endpoints. Once we have the endpoints, then all we need to know is which is on top, and then we plug it in. The area is going to be integral from the bottom to the top of the region of the top function, x, minus the bottom function, x squared, dx. Well, anti-differentiate this. We can do that. Anti-differential of this one is going to be 1/2 x squared minus the anti-differentiation of that one, 1/3 x to the 4th. Going from 0 to 1, we plug 1 in, we get 1/2 times 1 squared minus 1/3 times 1 to the 3rd. Minus plug 0 in, you get 0. Do it, get a common denominator and all that sort of stuff, we end up with 1/6. This may look like more than 1/6, but remember, this whole thing right here is the unit circle. So that area is 1/6. I'm sorry, not the unit circle. That's the unit square. It's late. So anyway, this is 1/6 of that total area. That's how you do it. How else do you do it? Let's try another example. Let's skip this one for a moment and come over to this second one. I want to find the area between, these are also easy functions. Y equals x to the 5th. Let's draw them. Here's the one, and here's the other. Look kind of like x cubed, but it's even steeper. And it should tell you there are two regions, and the thing that's on top in one of them is not the same as the thing that's on the top in the other one. How do you find the solutions of where this and this and this are? We do it the same way. X equals x to the 5th. Bring that over. 0 equals x to the 5th minus x. Factor the x out. Factor. This is the difference of squares. Factor again. If we set that to 0, we get x equals 0, x equals plus 1, or x equals minus 1. This is never 0. So those are our 3 points. Now, which is on top? Here, y equals x is on top. Here, y equals x is on bottom. So how do you solve for the area? Well, the area is going to be each piece separately. From minus 1 to 0, it's going to be the top one, x to the 5th, minus the bottom one. From 0 to 1, it's going to be the top one, x, minus x to the 5th, the bottom one. Now, I could just do both integrals separately. And often that's what you want to do, because the shapes and the details often are different. But in this case, these are both odd functions. There's symmetry going on. That shape is exactly the same as that shape, which means the area in each of those is the same. I don't have to do this twice. Each one's going to have the same area. So I can save myself a little time. Just make it 2 of one of these, say 0 to 1. X minus x to the 5th here. Anti-differentiate. Keep that 2 now. It's 1/2 x squared minus 1/6 x to the 6th. Going from 0 to 1. I'm going to have a very similar thing. When I plug 0 in here, I'm going to get nothing. When I plug 1 in here, I'm going to get 1/2 minus a 6th. That's a 1/3. Multiply by 2. You're going to get 2/3. That's how much area there is between both of these put together. And again, that's a unit box, so you can see if I put that there, we have 1/3 of that total box is the total area. Hopefully this makes some sense. The trick here is twofold. One, sometimes one's on top and the other one's on top in a different part. The other thing is finding all of the endpoints. Factoring this is not necessarily easy, but usually it's pretty straightforward. If you graphed that and you saw there were exactly 3 points, you could also do it by knowing there are 3 points and just reasoning out what they are, testing them out. You can say 0 is one of them. Well, is it? Yes. One of them. Is 1 an answer? Yes, they're the same. Is minus 1? Try it. It is. I know there are 3. Those are the 3. So that's one way you could do it sometimes also. Let's try, however, a third example that will go a little beyond this. I don't want to just go between 2 functions now. I want to find the region bounded by 3 functions. Here's one of them. Here's one of them. Here's one of them. I don't know exactly what this looks like. So let's graph. That's usually the best choice when you're not sure what you're doing. Y equals 1 is easy. Y equals x squared is easy. And y equals, well, 6 minus x is actually pretty easy too. This is the region. Now, I want to go from top to bottom. Clearly, these two are the top. One of them, this is on top of the first half, that's on top of the second half. This is always the bottom. So that's not going to be a challenge. But what is a challenge is, how do you find the points? What is this endpoint? What's that endpoint? And we have another point in the middle here that we have to figure out what to do about. Well, this one right here is where these 2 functions intersect. The x squared and the y equals 1. Let's do that one first. 1 equals x squared. Well, that actually happens in 2 different places. So maybe I could do that. But I'm talking about this region right here. So this point over here is not important. That one is. Factor it. You can show x is 1. What about this one over here? That's also fairly easy to do. That's where we have the y equals 6 minus x. I'm sorry, that's not that one. That's this one. Y equals 6 minus x, and the y equals 1. 1 equals 6 minus x. We'll just do that. X is going to be 5. Hopefully you can realize that this point's going to be somewhere in between 1 and 5. It's where this and this are the same. X squared equals 6 minus x. That's a quadratic. It actually has 2 intersecting points. If this continues on, we get to here. And there's a point over here somewhere. But that's also not part of the region we want. I guess you could argue that maybe this region was what it was. Maybe this problem could be better worded. So we could say the region in the first quadrant That'll fix the issue. But if we got that, we only want x equals 2. Okay, so we know this is 2. How do we put it all together? How do we find that area? Well, what's on top? What's on top differs in here before 2 and after 2. So we'll break this into 2 integrals. Not because it's the number 2, but because we can break it into 2 separate pieces. So the area is going to be the integral from 1 to 2 of top minus bottom, dx, plus integral from 2 to 5 of top minus bottom, dx. Well, in the first part, from 1 to 2, the top is x squared, the bottom is 1. From 2 to 5, the top is 6 minus x, the bottom is 1. So how does this all work? Well, now we have just integrals to do. We can anti-differentiate this. This is 1/3 x cubed minus x, evaluated from 1 up to 2. This is, well, 6 minus 1 is 5, so we'll get 5/2 x squared. I'm sorry, no we won't. It's 5 minus x. We get 5x minus 1/2 x squared, evaluated from 2 to 5. This is not a case where one of the two things becomes simple and 0, so we're going to plug it in carefully. I'm going to plug 2 in first. For the first part, I get 2 cubed is 8/3. 8/3 minus 2. That's the first bit. Plug in 1. We're subtracting that off. It's plug the 2 in, we get something, minus plug the 1 in, we get something. 1 goes in there, we get 1/3 minus 1. And that is this whole integration. Now plus. Plug 5 in here. I get 5 times 5 is 25. Minus 1/2 of 5 squared, so 25/2. Minus, plug 2 in. 5 times 2 is 10. Minus 2 times 2 is 4/2. How does this all work? I get 8/3 minus 1/3. I get 7/3 all told. Minus 2 minus minus is, so plus 1 is minus 1. Plus 25 minus 10, so plus 15. Minus 25/2 minus minus 4, so minus 21/2. What is that? 15. Well, here, let's put this up here. 15 minus 1 minus 10.5. And then plus, what's 7/3? It's 2.333 repeating. 15 minus 10.5 is 4.5, minus 1 is 3.5, minus that, or plus that. 3.5 plus that is 5.8333. That's how much area we have here. Now, this doesn't look like as much area as we had before, so that's kind of surprising. It's so big. But remember, this is kind of large. This is 4. It goes all the way to 5, goes all the way up to 4, but it's only a piece of that. So that's how it works. This is a harder one. It's as hard as we're going to get. Until next time, this is Dr. Jet.